So now we're getting into looking at derivatives and using those for application problems. And so right now what we're going through is the sections that we covered in our chapter 6 of our textbook. And the following says, finding absolute extrema. So we looked at the extreme value theorem, which says that if we are on a closed interval, so it says to find absolute extrema for a function, f is continuous on a closed interval AB. If that is the case, then it has to have an absolute max and an absolute min, and that, could occur at one of the endpoints. So first thing you want to do is find all the critical numbers of f that fall in that interval, not necessarily including AB. And then evaluate all those critical numbers in AB, and you're plugging that in the original function, not what we were doing before to test if it was increasing or decreasing. We're just going to go back and plug it into our original function. And we're also going to evaluate the endpoints on AB, because it's possible that absolute extrema happens at one of the endpoints of our closed interval. And then you're plugging that back into your original function. And so you're looking for the smallest and largest values that you found in step 2 and 3. And that would be the absolute max and absolute min is the y value. And where it occurs is the x value. So once we looked at finding absolute extrema, then we looked at applications of solving extrema problems. And doing that, you got to read your word problem carefully, maybe multiple times. Make sure you understand it, what is given and what is unknown and known. If possible, it's helpful to make sketches or draw a diagram, label different parts of that diagram, decide which variable must be maximized or minimized, express that variable as a function of one of the other variable. So you might have multiple variables in there. And so we're going to rewrite our thing that we're trying to maximize or minimize in terms of one variable. Find our domain, find our critical points. If the domain is a closed interval, evaluate the function at the endpoints at each of the critical numbers to see if it yields an absolute max or min. If the domain is an open interval, apply critical points when there is only one critical number. The critical point theorem, sorry. If there is more than one critical number, evaluate the function at the critical numbers and find the limit as the endpoints of the interval are approached to determine the absolute maximum or minimum exist at one of the critical points, is what that should say. We then looked at implicit differentiation. This is where we had an implicit equation where we had x and y on both sides of the equation, and we went ahead and differentiated both sides. And we then could find dy dx. So to find dy dx for an equation containing x and y, you're going to differentiate both sides of the equation with respect to x, keeping in mind that y is assumed to be a function of x. So we had to use a chain rule whenever we took a derivative with respect to y and tack on that dy dx. So place all terms with dy dx on one side of the equation of the equal sign, and then all the terms without dy dx on the other side. We can solve for dy dx by factoring out dy dx and then dividing both sides by whatever that factor was. So you get dy dx by itself. Implicit differentiation helped us when we got into the next section, which was on related rates. Related rates, so our variables normally were with respect to time. So we maybe had multiple variables. X was respect to time, Y with respect to time. And so when we differentiated both sides of our equation, we had to keep that in mind and tack on either dx dt or dy dt, depending on what variable we were differentiating with respect to. Okay, so solving related rate problems, identify all the given quantities as well as the quantities to be found. Draw a sketch when possible. Write an equation relating the variables of the problem. use implicit differentiation to find the derivative of both sides of the equation with respect to time. And then we're going to plug in what we know, solve the derivative, giving the unknown rate of change, and substitute the given values. Okay, so that was a quick review of what we covered in chapter 6 and what you need to know how to do. So the first example I have here is a picture of a graph, and looking at the graph, you should be able to find, if it exists, absolute max, absolute min. So looking at that first graph on there, we want to know, is there an absolute minimum only? Is there no absolute extrema? Is there an absolute minimum and an absolute maximum, or just an absolute maximum only? We know both graphs are the same. So I copied the wrong thing. Okay, so I got the correct second graph up, and then you guys were able to respond a little bit inside the chat. And so there was a comment that this is neither, right? Because there is open circle, and that is correct because the theorem says we have to have a closed circle as be continuous on a closed interval. And so there's no value that I am hitting that is the smallest. Any value I choose of x really close to a, I can get a little closer to a to get a smaller value. Same thing with this, any value I choose near x equals b, I can always get closer and closer to this open circle, but it's always getting larger and larger. So there's no one specific value. And so in this case, this has no absolute max or absolute min. And so looking at the second one, does it have an absolute max or an absolute min? Or does it have one or the other, or both or neither? Okay, so this one is an example too, where we have open circles. But notice that we have a highest point that is at a point that is not at an open circle. And so that's the highest point on the graph. So this is actually, maybe you call it C. And maybe we call this f of x. So f of c is an absolute max. And then if I look at it, there is a closed circle, and it's defined when x is a, that is the smallest value that this graph hits. And so f of a is actually an absolute min. So in this case, that theorem, it didn't hold true where it was a closed interval, where it was continuous. It was an open interval, but it still exists. Okay, so same sort of example. We're trying to see if there's any absolute max, absolute min. We're given an equation though. So we have g of x is equal to negative x squared plus 7x minus 12. And we want to find the absolute max, absolute min on the interval 4 is less than or equal to x is less than or equal to 3. Which I think is a typo. Right? Doesn't that not make sense? Or if this is correct, another way to write this is x has to be greater than or equal to 4, or x is less than or equal to 3. And if that's the case, then we may or may not have a closed interval. I mean, we have closed interval, but there's jumps. And it's going to negative infinity and positive infinity. So let's first look at this where this is maybe written differently. And then if we want, we can come back and look at it the other way. Let's say that this was just 3 is less than or equal to x is less than or equal to 4. So this is a continuous function. We want to find our critical numbers, and we can do that by finding our first derivative. And so looking at this, I get the first derivative is negative 2x plus 7. We want to find when this is equal to 0 and where it's undefined. Well, it's defined everywhere, but our derivative is equal to 0. Let's subtract 7 on both sides. So we get negative 7 equals negative 2x. Let's divide both sides by 2. So we get x is equal to 2 negatives make a positive when we divide, so 7/2, which is equal to 3.5. You have to make sure that the critical number falls inside of the domain that we're looking at, which it is if we look at it as 3 is less than or equal to x is less than or equal to 4. So with the extreme value theorem, we're plugging this back into our original function. And we're trying to see what is the smallest y value we get back and what is the largest y value we get back by plugging in our critical numbers and the endpoints of the intervals. So we're going to plug in 3. We're going to plug in 3.5 wherever we see an x, and we're going to plug in 4 wherever we see an x. And we're going to see what we get back. So if we square 3, we get 9. So we get negative 9 plus 7 times 3, 21 minus 12. So if we sum that up, negative 9 minus 12 is negative 21, and negative 1 plus 21 is 0. So g of 3 gives me back a y value of 0. So I'm going to do the same thing, but now I'm going to plug in 3.5 wherever I see an x. So if I take 3.5 and I square it, I get 12.25, but I have a negative in front. So negative 12.25 plus 7 times 3.5, which gives us 24.5 minus 12. Okay, so that here, adding my two negatives together gives us negative 24.25. And subtract that from 24.5, that would give us a 0.25. Now we're going to go in and plug in 4 wherever we see an x. So 4 squared gives me 16 with a negative in front. So negative 16 plus 4 times 7, so plus 28 minus 12. So this is negative 28 plus 28. This gives me 0 again. So we're looking at the smallest y value that we get back. The smallest y value occurs twice, and that is at 0. So we have an absolute min of 0, and that occurs at x equals 3 and 4. And we have an absolute max. So the highest y value we get back is 0.25. And that occurs at x equals 3.5. So if we looked at the problem where it was 4 is less or equal to x, which is less than or equal to 3. Like I said, this would have changed where this would have been, well, to me, it's easier if I write it like this. X has to be less than or equal to 3, or X is greater than or equal to 4. We have in values here, but this is like coming from negative infinity to positive 3. Union, another way to write this, 4 to infinity. So we want to see what's going on with our n behaviors of our graph. And so let's look at the limit as x approaches negative infinity of g of x. And let's see where it's shooting. Is it shooting up or is it shooting down? And so we can think about this. If we have this negative in front, we square a negative infinity. That's just going to be huge, huge numbers, keep on growing, plus 7 times negative infinity minus 12. And so basically I have negative infinity and infinity minus 12. This whole thing is going to negative infinity. And so it's shooting downwards. And then when we hit x equals 3, we got a y value, right, of 0. And then at 4, we also had a y value of 0. Well, let's go ahead and let's go in and plug in positive infinity. So if we look at the limit as x is going to positive infinity of g of x. So we have negative infinity squared plus 7 times infinity minus 12. Well, this square piece, this is negative infinity squared, which is growing faster than this positive piece. And so since that's the case, this is going to negative as x goes to positive infinity. So this would be shooting downwards here. So if we think about it this way, and we already tested for our critical value, we found that g prime of x was equal to 0 when x was 3.5, or we can just say 3.5. But that 3.5 is not in our domain. And so looking at what we have here, notice that there's no absolute min. But we do hit a highest value. We have an absolute max in this case of 0. And that occurs twice at x equals 3 and x equals 4. So things changed when the domain of my function changed. So here's a word problem, application problem using absolute max, absolute min, or local max, local min. So the problem says find the number of units that must be produced and sold in order to yield a maximum profit given the following equations for revenue and cost. And so we want to look at what's going to give us the maximum profit. And profit function, this is equal to how much money we're bringing in, our revenue, minus how much it's costing to produce our product, which is C of X. So we can find our profit function because we're given both of those equations. So we have 30x minus 0.5 x squared minus the cost function, which is 2x plus 8. So make sure there's brackets around that whole cost function because we got to distribute that negative sign. So we're given that our profit function, P of x, let's just rewrite this descending order of powers. So we have a negative 0.5 x squared. Here's a 30x. This is going to be a minus 2x, so that's a plus 28x. And now this is a minus 8. So here's our profit function. Value of x has to be greater than or equal to 0. Doesn't make sense to have negative items that you're selling or making. And now we want to find any critical numbers. We're going to find out when this is equal to 0. Finding when the derivative is equal to 0. So taking the derivative. So this is negative 1/2. It's another way to write that. That helps you. And if we bring down our power of 2, notice that that cancels with it. So we would have negative x, subtract 1 from our exponent, which is 1, plus the derivative of 28x is 28. So we're looking at when is negative x plus 28 equal to 0. So that's when x is 28. So we need to make sure that this is a max. So there's a couple ways that we can do this. We can use the first derivative test and find where it's increasing or decreasing, or we can use a second derivative test, which is going to be a lot faster in this case. So taking the second derivative of P of x, we get negative 1. Notice this is always less than 0. And so this tells me that it's concave down everywhere. And so at this point where I have a horizontal tangent line is a max. So that tells me how many items need to be sold and find the number of units that must be produced and sold in order to yield that. So we found that it's when x is 28. If it asked what is the maximum profit, then you would have to go back in here and you would have to plug that back into our function of P of x. So we would look at P of 28 and see what we got back. And that would be the maximum profit that we would yield. But the question just wanted to know the number of units. So looking at one more example, and this deals with related rates and implicit differentiation. So a company knows that the unit cost C and the unit revenue R, the production and sale of X units are related by the cost C equals R squared all over 122,000 plus 11,397. So we want to find the rate of change of unit revenue. So we want to find the rate of change. So that tells me derivative of the revenue. So dr dt. When the units cost is changing by $11 a unit. So the cost is changing. So I'm thinking of that as a rate. And so I know that d, the derivative of the cost function with respect to time, is equal to $11 per unit. And the unit revenue at that time is 1,000. So I know here R of 11 is equal to 1,000. So all we're going to go through and do, we're already given an equation. We're just going to go through here and we're going to take the implicit differentiation and we're going to differentiate both sides. So the derivative of C is just 1, but that was with respect to time. It's a function with respect to time. We need to use the chain rule. And so we tack on that dc dt is equal to, so now taking the derivative of this r squared over 122,000. Well, think of that as 1 over 122,000. That's just a coefficient in front times the derivative of r squared, which we know is 2r, plus the derivative of a constant is 0. We took the derivative, of with respect to r, so we can't forget to tack on that dr dt. So all we're doing now is we're going back in and we're replacing what we know. So we know that dc dt is 11 is equal to, well, this can simplify a little bit, right? 2 goes into 122,000, 61,000 times r. But r we're given when t is 11, c is 11, dc is 11 is 1,000. And times dr dt. Well, that's what we're trying to find. This seems way, something's off. Oh, I know why. I was going to say this is something's off because this is way too small. This should have been 1 over 61,000 times 1,000. So let's simplify this a little bit more. 3 zeros cancel. So this is really dr dt is equal to 11 times, we can multiply both sides by 61. So 61 times 11 gives us 671. So the rate of change of our revenue is $671 per unit. When the rate of change of our cost is $11 and our revenue is 1,000.